Hello everyone, this is Professor Ng Chi Kun from Milimas. In this video, I'm going to show you some tutorial solutions on conjugate beam method. So the first question that we are going to look at is a cantilever beam with loadings as such. So now we want to determine the slope at B and the maximum displacement of the beam. So maximum displacement will be considered the maximum at C. So use the conjugate beam method. So take Young's modulus as 200 gigapascal and moment of inertia as 550 times 10 to the power of 6 millimeter to the power of 4. So for this beam here, first of all, we draw the free body diagram to determine the reactions first. Okay, after that, we draw the bending moment diagram and we get all bending moment as negative bending moment. So we have negative bending moment diagram with maximum moment of 180 kilonewton meter at the fixed support. Next, we draw the conjugate beam. So the real beam has a fixed support here, so it becomes free in the conjugate beam, and then the free end in the real beam becomes a fixed end in the conjugate beam, and then the loading is the M of the EI diagram. So all bending moment is negative, so the loading from M over EI is downward. So first of all, we determine the slope at B. So for the slope at B, we calculate the shear at B. So if we cut across this section and isolate this as a free body diagram, we'll get this diagram here. So over here, on the right hand side, our shear is downward as a positive shear force, and the moment anti-clockwise moment is a positive bending moment. MB prime. And then on this segment here, we have two resultant forces, one from the rectangular part of this distributed force, and then another resultant force is from this triangular load. Okay, so let us first look at the rectangular load. So this rectangular load is 135 kilonewton meter, okay, multiplied by 1.5 meters. So it is 135 kilonewton meter multiplied by 1.5 meters. And then the distance from point B to the location of this resultant force here is half of 1.5 meters. Next, we look at the resultant force from this triangular load here. So this triangular load here, this is 45 kilonewton meter over EI. So we have 45 kilonewton meter over EI times 1.5 meter times half, because it's the area of a triangle. And then the distance here is 1/3 of 1.5 meter. So meaning that on this side, the distance is 2/3 of 1.5 meters. So if we want to know what is the slope at B, then we calculate what is the shear force in the conjugate beam, BB prime. Okay, so we sum all the forces in the vertical direction, and we have VB prime, which is downward, so negative BB prime. And then we have this force here, which is also downward, so negative of this force here. And then we have another force here, which is also downward, so negative of that force there. So there is no other forces in the free body diagram, so it's all equal to 0. And then theta B is equals to BB prime. So we have minus 236.25 kilonewton meter square over EI. So we have 945 kilonewton square meter over 4 EI, and then this is clockwise. We got rid of the negative sign, and then we put in the direction of the slope or the rotation at B, which is clockwise. So we substitute E and I all converted into Newton and meter, so we get 0.00125 radian, which is clockwise. Next, we determine the maximum displacement. So we know that the maximum displacement is at C. So we cut across section C and isolate it as a free body diagram. So we have VC prime, which is downward as a positive shear force, and anti-clockwise moment or a counterclockwise moment of MC prime as a positive bending moment. And then the beam is loaded with M over EI diagram. So this is the whole M over EI diagram that we have determined just now. So in this case, we have three resultant force. The first one is from this triangle here. Second is from this rectangle there. And then the third is from this triangle here. So we have already determined these two in the previous solution. So we just need to determine what is this resultant here. So this resultant here is 45 kilonewton meter over EI, okay, multiplied by 1.5 meter here, and then multiplied by 1 over 2 because it's the area of a triangle. So we get this resultant force as such, and then the distance from here to here is 2/3 of 1.5 meters. And then this distance here is 1.5 meter plus the distance that we have determined previously, and also this distance will be 1.5 meter plus the distance that we have determined previously. So to get the displacement at C, so we calculate the moment at C prime. Okay, so we calculate MC prime. So we sum moment at this point here. So when we sum moment, MC prime is counterclockwise moment, so it's positive MC prime. And then we have a moment due to this force, which is also counterclockwise with respect to C prime. So it's half of 45 kilonewton meter over EI times 1.5 meter multiplied by the moment arm of 2/3 of 1.5 meters. So the next force that we look at is this force, which causes counterclockwise moment with respect to C prime as well. So the force magnitude is this term here, which is this term here, and then multiplied by the moment arm of 1.5 meters plus half of 1.5 meters to give the moment. And then the third moment that we look at is produced by this force here with magnitude of this much, and then multiplied by the moment arm to C prime. So it's 1.5 plus 2/3 of 1.5 meters, and is a counterclockwise moment. So it is also positive. And then there is no other moments, then we equate them to 0. So solving for MC prime, we get negative 573.75 kilonewton meter cube. So by converting it to fraction, we have 2295 kilonewton meter cube over 4EI. So we substitute EI by converting all the forces and dimension to Newton and meter. So this one kilonewton converted to Newton, we multiply by 10 to the power of 3. And then gigapascal is in Newton per square meter, so no conversion here. And then for the second moment of area, the conversion is multiplied by 10 to the power of minus 12. So in resultant, we have 10 to the power of minus 6. And then we get 5.216 times 10 to the power of minus 3 meters, so it's 5.22 mm. So just now we got negative, meaning that the deflection is downward after we have changed it to the magnitude. Okay, so meaning that the deflection is downward of 5.22 mm at C. So that is the maximum displacement at C. For the next tutorial question, we look at an overhanging beam A, B, C with the loading as such. So we use the conjugate beam method, and EI is not given, so we just leave EI in the solutions. So these are all 3 meters. Okay. So first of all, we determine the reactions. Okay. So we draw the free body diagram for the beam like this. So the reaction here is 105 kilonewton upward, and then the reaction here is 15 kilonewton downward. So when we want to draw this bending moment diagram, we draw them by parts. So first of all, we assume that this 30 kilonewton force is not there. We have only this 60 kilonewton force. So when you draw the bending moment diagram on this beam due to this 60 kilonewton force, and when we cut across this section here, we get a beam cross section like this. So this is M, and this is V, and this is 60 kilonewton, and this is X. So this bending moment M is minus 60 X, where X starts from the origin and measured from right to left. So here we'll get negative bending moment of 60 times X, and the maximum moment occurs here, where the maximum moment is 180 kilonewton meter, but is negative. In terms of magnitude is the maximum of 180 kilonewton meter. And then it will reduce to 0. So that is the first bending moment diagram that we have drawn based on this 60 kilonewton force. And then the second bending moment diagram that we draw is assuming that this force is not there. Okay, so meaning that this part of the beam is redundant span. So it becomes a simply supported beam like this. And then it's 0 moment O on this side of the beam. So we can consider that the overhang is a redundant span. So we can get rid of that because there is no force over here. We got rid of the 60 kilonewton force. So in this case, the force is acting at the center of the simply supported beam. So meaning that the maximum moment is PL over 4. So P is 30 kilonewton, L is 6 meters. So P times L is 180 divided by 4. We have 45 kilonewton, and this is positive bending moment. So we have a bending moment diagram which is positive like this. So this is positive bending moment. This is negative bending moment drawn just now. So now we have got all the bending moment diagrams. We can put all these bending moment diagrams over EI onto the conjugate beam. So for the conjugate beam, originally this is a pin, so it's still a pin, and then this is internal roller becomes a hinge, and then this is a free end, so a free end becomes fixed. So the conjugate beam looks like this. So here is pin, over here is a hinge, and then over here is fixed. And then positive bending moment, the loading on the conjugate beam becomes upward. And then for negative bending moment, the M over EI, which is the loading on the conjugate beam, becomes downward. So first we determine the slope at B. So when you want to determine the slope at B, we can detach this pin here and then isolate this as a free body diagram. So at the hinge, we know that the moment is 0. So there is only a shear force at hinge B prime there. So we have a shear force By prime. So from this triangular load here, the magnitude of the force, or the magnitude of the resultant force, is half times the height of 45 kilonewton over EI multiplied by the base, which is 6 meters. And then for this force here, we have the area of the triangle like this, which is half times 180 kilonewton meter over EI here, and then 6 meters is the base. And then the distance of this force from A prime is 2/3 of 6 meters. and then the distance of this force to AY prime here is 3 meters. So to determine BY prime, we can sum moment at AY prime here to get rid of this force AY prime. Supposedly there is a reaction at this pin here. This is a pin support in the conjugate beam. So when we sum moment at A or A prime, we get By prime times 6 meters, which is a counterclockwise moment, so it's positive here. And then the next force that we look at is this force here, which has a magnitude of this, okay, over here. And then multiplied by the moment arm of 3 meters, and then this is a counterclockwise moment with respect to point A or A prime, so it's a positive bending moment. And then the next force that we look at is this force here with magnitude of so much, and then the moment arm of 2/3 of 6 meters, and then it's a clockwise moment, so negative. So there is no other moment, so we sum all these moments and equate it to 0, and we get By prime of positive 5 kilonewton meter square over 2EI. So the positive value, meaning that the assumed direction is correct for By prime. So By prime is upward in this case. So bear in mind that at this hinge here, By prime is upward, and if we take this side of the free body diagram, okay, where we have the bending moment and shear force like this, and then the By prime has to be downward, because these two forces are complementary to each other. If it's upward on the left hand side of the free body diagram, it must be downward on the right hand side of the free body diagram, as what we will see later. So next we cut across a section here to see what is the shear force at joint B there. So the free body diagram will look like this, where By prime has already been solved just now, and then the shear force on the left hand side is upward for the shear force as the positive shear force for BB prime. Okay, so from this free body diagram, when we sum all the forces in the vertical direction, we have BB prime plus BY prime is equal to 0. So BB prime is minus 5 kilonewton meter square over 2EI, and then we just take the magnitude, and the negative means that it's a clockwise rotation in slope or rotation for theta B. Next, we want to determine the displacement at C. So for displacement at C, we need to isolate this part of the beam as the free body diagram. So at the fixed end here, we have the bending moment and shear force, and at this hinge here, we have By prime. So By prime from the other side, we have got upward By prime. So the By prime on this side of the free body diagram has to be opposite of the By prime in the other free body diagram, because they are complementary forces, so that when they are joined together, both of them will cancel off each other. But the magnitude is the same, so here we have a downward By prime forces. And then for the shear force at C prime, we have shear force in this direction as positive shear force, and then bending moment in this direction as positive bending moment for the MC prime. And also the shear force is BC prime downward. So on this free body diagram, we have this triangular load, and then when we calculate the resultant, it is 180 kilonewton meter over EI here, multiplied by 3 meters multiplied by half. Okay, so that will be the magnitude of the resultant force of the triangular load there. And then the distance here is just 2/3 of 3 meters. So next we sum moment at point C here. So first we have this MC prime, which is anticlockwise, so positive MC prime. And then next we have this force By here, which has an anticlockwise moment with respect to point C, so it's 5 kilonewton square meter over 2EI times 3 meter, which is the moment arm. And then we have this force here with so much magnitude, and then it causes an anticlockwise moment with respect to point C prime as well. So the force multiplied by the moment arm of 2/3 of 3 meters will be the moment caused by this force here. And then there is no other forces causing moments, so we equate everything to 0. So the solution gives us MC prime equals to minus 2835 kilonewton cubic meter over 2EI. So it's equals to the magnitude of 2835 kilonewton cubic meter over 2EI, which is downward deflection for joint C. So meaning that the deflection here is downward with a magnitude of 2835 kilonewton cubic meter over 2EI. So that's all for this tutorial session. Thank you very much for listening.